Right, good morning, good afternoon, whatever time of day it is. It's morning here. I've woken up because I'm recording this quite early in the morning because obviously it's finally reached that point when summer started and it's at about 1000% humidity or whatever it is that it's impossible to sleep in. So I'm up early and I'm going to start recording lectures this week on the proper propeller theory. So we've got to go through quite a lot of heavy theory at the start of this week. It all comes down to understanding two diagrams, really. There's a lot of non-dimensionalization that we use in propeller theory, and we're going to cover things today. There's going to be quite a few new terms introduced, but as long as you understand the fundamentals of the blade element diagram, we're good. There's one place that I've not managed to marry the theory perfectly between propeller and rotorcraft theory, and it's down to the dimension x, and I'll mention when I get to it when it can be a little bit confusing, because later on in the course we're going to set axis systems for our propeller disc and our blade axis, and we'll define x as being the flight direction. We also, for propeller theory, define x as a non-dimensional span-wise ordinate. It's going to be very clear when we're using the two and in which context, and I'll try and come up with a means to marry those two up properly, but for the time being I'll just probably use it for both. But it'll be clear from my usage which one I'm actually referring to. So let's go through the very basics of propeller theory, and we're going to start out with some facts about propellers basically. Let's write propellers properly. So propellers converts engine torque into propulsive thrust. That's their job. An engine doesn't produce thrust, an engine produces torque, and then it's able to, the propeller itself turns that into thrust, which is useful for our aircraft. They are very efficient at moderately high subsonic aircraft speeds. So we're talking about Mach 0.6 to Mach 0.7. If we go much further above that, then we reach compressibility issues. The tip of the propeller is effectively going into a transonic region, even though the aircraft itself isn't. So we're going to say they're very efficient at these speeds, and they become less efficient as we speed up. Their mechanism of action and why they're so efficient is that they provide a small velocity increment but they provide it to a very large mass of air. And we can appreciate this if we look at the frontal area of a propeller on an aircraft like an A400M or any of the aircraft that I had in the last lecture. Then the disc area is larger than a comparable turbojet, so it's providing a small acceleration to a large mass of air, and that's one of the reasons why they're so much more efficient. We're not going to get too much into into the theory of this part just yet, but effectively we get thrust from providing a momentum increment to the fluid. That's Newton's second law. Thrust is the rate of change of momentum, because force is the rate of change of momentum. It doesn't help us at all if we also provide kinetic energy to the air. Remember, kinetic energy is half mv squared. If we provide kinetic energy to the air, which we will have to be doing, that's a loss. So we try and mitigate that by providing a small velocity increment. So we've got a moderately large mv, and we'll then have a smaller half mv squared, which is the kinetic energy. We'll go more into that a little bit later, but this is the idea about why they're efficient, is because of this fact here. By contrast to a turbojet, which provides a very large velocity increment to a small mass of air. So those are our propeller facts. We're going to look at some nomenclature. So let's draw an aircraft wing. So I've just drawn the port wing of an aircraft. So we're going to put the aileron on there. So we've got the aileron which tells us the flight direction. So this is then oncoming velocity. Let's make myself even smaller. I don't need to be big in this anymore, so let's move me down. There we go. Okay, so we have, this is our aircraft wing, and then we can define a propeller to be sitting somewhere on this wing. I'm not the best artist, but I can do a reasonable job of drawing this. So we have got a disc, and this is our propeller disc. Disc spelt with a C. I'm pretty sure that's the same in US English as it is in British English. Disc, by contrast to a hard disk. A hard disk of a computer would be spelt with a K. Disc with a C is a contraction of Latin for discus, or it might be Greek, I don't know. But anyway, so disc is spelt with a C for our purposes. We've got normally a spinner at the center, at the hub. So this is a rotating part that's shaped like a cone. Let's try and put some shading on this to make it look more like a cone. We can then define the spinning axis of the propeller. Let's draw this in here. So this is the line that the propeller spins around. So I'm going to put let's draw my rotation here. So I'm going to put rotation. So this line that I've drawn through there, we can call the propeller thrust axis. Okay, and we're going to say that's PTA, propeller thrust axis. We could also define this as the rotation axis. We'll use those two terms sort of interchangeably. We're then going to draw some blades on it. The propeller won't do anything without blades, so let's draw one on. We've always got at least two. Let's draw two blades on here. I'll draw one at the top and one at the bottom. So if it's spinning round clockwise when viewed from the front, this defines my azimuthal direction. So the propeller's spinning around, I then define a rotational coordinate system, which we give the symbol psi. This is my azimuthal direction. And we've then defined another quantity here. We've defined the propeller radius, which we give the symbol big R. So this line that's extending through each of the blades defines another axis for us. This defines the pitch change axis, PCA. So we can appreciate it's called pitch change because propeller blades are variable pitch. So it means they can spin around on their axis like this, which enables us to change the relative angle of attack of all of these sections at once. So that axis that goes, this is a swept blade, so the pitch change axis would be a straight line down here. That's my PTA or pitch change axis. What else can I define on here? So we've got our radius that's been defined. We're going to define a radial position as well, because it would be useful to be able to define different parts of the blades as in terms of their location from the hub, which is the very center. That's probably worth mentioning as well. So let's say right here, that's the hub, which is the center, and this body here We're not going to really look at the spinner too much, but that's called the spinner, which is just an axisymmetric body that provides a mechanism to cover all of the, or a fared body around all of the complex machinery that deals with the pitch change. We're then going to say, okay, well, if I want to define part of the blade through here, this we're going to say exists at some radius, and we're going to give this a symbol lowercase r. So this defines my radial ordinate, or radial position, we'll say. So we've got uppercase r, which is the total radius, which is a single number, and then lowercase r is the radial ordinate. So it can vary from 0 at the hub up to whatever the value is at the tip, which is our radius value. We cannot define this as a dimensional. But it's often, and in a lot of legacy propeller text, we'll define it in a non-dimensional form. So if we're going to non-dimensionalize our radial ordinate, it would make sense to make it go from 0 to 1. So 0 at the hub to 1 at the tip. So then we're going to define x is equal to r divided by r. So this value here, radial position, this value here is the actual, just the radius. So the radius of a propeller might be something like 1.5 meters. And then we can then have a non-dimensional radial ordinate that can vary from 0 up to a value of 1. Now, because we have the spinner here, our first part of the propeller blade is often at some value greater than 1. So it's maybe varying from 0.2 up to 1 for a propeller with a spinner in. And this is the bit here. This can just be a little bit confusing in some of the later ordinates. I maybe should call this X bar or something if I were to write a textbook, but we'll just call it X for the moment. This is the non-dimensional radial ordinate, not to be confused with the actual X axis, which we'll use when we define our axis systems later. But this is my propeller disc, and we're looking at it. So we've got the azimuthal direction that's been defined, we've got the radial direction that's been defined as well. I spoke a little bit about yesterday, but we can define the total inflow. And remember, inflow is the combination of incident velocity plus induced velocity. So incident velocity is whatever the propeller would see were it not there. So if we were just, say, traveling at some flight speed and there was a combination of flow field around the aircraft, this would give us the incident velocity. The propeller itself causes an acceleration. That's what happens, that's how it works. And that gives us the induced velocity. So we add these two together and we get the inflow. And we're going to really come back to this idea of inflow and how we can determine it, how we calculate it, and how we can infer things from experimental measurements thereof. So we'll come back to that a lot later, but we're just including it on here to say, okay, well, inflow is my velocity field. It's actually three-dimensional. Not worry too much about that. I can just put 3D down here, but we can just treat it as the velocity arriving at the propeller field. So this is my propeller disc. Now we're going to go through blade element theory first. So blade element theory, if we remember from the timeline yesterday, was actually developed after momentum theory. And certainly when I was an undergraduate, I learnt momentum theory first and then I learnt blade element theory. I actually think it's more instructive to learn blade element theory first because it's the one that makes sense. We're going to be splitting up the propeller into a number of different slices, and we're then going to define what happens at each one of those. And then we can add the induced velocity from momentum theory. So we'll get to momentum theory a little bit later in the week. But for blade element purposes, we're going to say, well, what's occurring in this slice here? We'll take a cross section through there and we'll have a look. Just before we get there, I realise there's one more thing I need to define on here. So we've got rotation. Obviously, rotation is really important. That's how the propellers work. Let's define rotational speed. So rotational speed, we've got different measures that we define them in. Now, the following is my nomenclature that I've found useful to use and instructive. It's not necessarily the same as you'll find in every textbook, but it will help in this. There's 3 unit systems that we use for defining propeller speed. So I'm going to write them down here. So omega is the SI, well, sorry, it's in general, this is the symbol that we use for an angular frequency. So we define this as our rotational speed in radians per second. Now that's useful because that's an SI unit. It's the one that we put into equations and get other SI units out. So if we are using an equation, that's going to give us some form of velocity or some form of translational velocity. This is the one that we need to use. So we'll say we'll use this one if in doubt. Unless we have one of the other 2 that's been defined as being used. So then uppercase omega, this is just my shorthand for revolutions per minute. We often talk about rotational speed in revolutions per minute because that's quite useful as a sort of human understandable attribute. So we talk about, say, a scale model propeller might rotate at 6,000 RPM. Flight, something like a Doughty R408J goes at about 800 to 900 revolutions per minute. Unfortunately, or not unfortunately, pretty much never use this in an equation. This is just something that we talk about. So we'll say never use in an equation, unless that equation is one that converts from revolutions per minute into one of the other human understandable units. And this last one, N, this is in revolutions per second. This is effectively hertz, we can think of it about, but for propeller purposes, we talk about it in terms of N. Now, sometimes we use this. In fact, we use it quite a lot when non-dimensionalizing. So whenever we see an N, we know that our rotational speed must be in revolutions per second. If we're trying to determine, say, a tangential velocity, and we'll talk about that more later, this is the one that we want to use, okay? So we're going to be using this one later, and this one here, you'll often see listed in textbooks and in legacy data as the rotational speed, but it's not very useful in equations. So we'll be aware of it, understand how to convert between it and the other forms, but just be very careful with that one. So we've got our rotational speed defined. We're now going to look at this blade element, and this will give us the idea of blade element theory. So blade element theory. I can mostly do this from memory, but I just need a couple of prompts to help me. So let's draw our propeller blade. I've drawn my hub here. No, let's draw that as a circle actually. And then I'm going to draw my blade. Not a very pretty blade, but I've drawn it on there. We've got our rotational speed defined in radians per second, and we've then got some ordinates we can define from the center of rotation up to the very tip. This defines radius. We're then going to look at a blade element, a finite slice through this blade. And we'll say this has thickness, dr, and exists at location, r. So we're going to take a slice through the blade and we're going to see what happens in this two-dimensional section. So I mentioned yesterday that I hope you guys are sort of happy with lift and drag and where they come from. If you're not, then there's I would say, an excellent resource on the Slack page. It's one that I wrote for that pilot textbook. If we take a cross section through a propeller blade, then we'll get an aerofoil out. Normally we get quite a highly cambered and thin aerofoil section out. So let's just have a reminder of what those look like. So we've got something that looks like a sharp edge teardrop shape. This is my general aerofoil. We're not really looking at propeller stuff yet. This is just a bit of a reminder. We've got some oncoming velocity, v infinity, at some angle of attack. So we have a lift and a drag. So if we were to look at the lift versus angle of attack, we would expect our lift to increase until it doesn't anymore and it stalls. Okay, we have a relatively linear part at the start, and then we have a non-linear stall occurring. If we were to look at then, let's not worry too much about drag. Actually, we'll just look at lift on here because drag just comes out in the numerical part anyway. So if we can work out an equivalent diagram like this for our blade element, then that's going to help us determine the aerodynamic properties of our propeller. Because if we can determine what the lift and what the drag are, then we've got the two-dimensional forces occurring on this blade element. We can then convert those into the forces we care about for propellers, which are thrust and torque. So say if we can get the lift and drag, then we can convert them to thrust and torque and hence determine propeller performance. Now we've got to do a little bit more work than just saying we'll do it. We're going to have to go through and develop some diagrams for our blade elements and then work out how we can determine things. So we're going to assume that we can, if we know the angle of attack, we can get the lift and drag or lift and drag coefficients for our propeller blade. So we'll say we assume that we know our lift and drag coefficients as a function of angle of attack for all parts of our propeller blade. Now we don't necessarily know that yet. We're going to go through some methodologies to determine them. But we can, for the most part, just assume that we've got a lift curve slope of around about 2 pi, which we should know from thin aerofoil theory from 312. Okay, so we're going to assume we know those, we're going to develop a blade element diagram. So when we're drawing for an aerofoil, it's helpful to draw our aerofoil in that direction. I tend to draw my blade element diagram just in a slightly different orientation. So let's draw. I tend to draw it this way just because it's easier for me to draw an aerofoil in that direction. That's not a very good aerofoil. Let's draw a better one. Okay, that's an acceptable aerofoil. Okay, so in fact, let's just move this a little bit down the page. So this is my propeller blade. Now, my aircraft is flying from right to left. So then this defines my propeller disc. That's in the disc plane. And then that similarly defines my thrust line on the propeller. So this, we're going to draw this going this way. So this tells us then that this blade is if we were on this aircraft up here, then the way that I've drawn this means that actually the blade would have to be over here and we'd be looking at a section through it because it would be spinning round, traveling downwards. So we've got this on here and I'm just going to draw that blade motion on here. So we define two velocities that are going to help us, and I'm going to draw velocities on. I'm going to draw them all in black. So I'm going to say on this one we've got Vn, which is our normal velocity. And then down here we've got Vt, which is our tangential velocity. So we've got those two velocities. Vn comes from forward speed and the axial inflow. The tangential velocity is the air that's going towards the propeller blade because of blade motion. The blade is traveling downwards, so the air is going towards it. The aircraft similarly is traveling in this direction, so the air is coming towards it. So in fact, let's draw that on as well. Let's just draw aircraft motion. So then these two velocities, in fact, let's draw one more angle first. I'm going to draw if we were to draw our blade zero lift line, and let's pretend that crossed perfectly through the center. This is our blade zero lift line, and this means that the blade makes some angle to the disc plane. Now this angle in here is our twist, which we give the symbol beta. We'll talk about this a little bit more later, but we've got some. If we look at this blade here, we can see that as I go along, it's more twisted at the tip, more twisted at the root than it is at the tip. So I've got some part here, which is theta. It's just a function of r. This is the inbuilt twist. And we remember that the blade can also be pitched around the pitch change axis. So this is then, that part there is the pitch change axis value, plus whatever's there because of the twist of the blade. So we're going to call this one here setting, and this one here is twist, which gives us the total blade twist angle. So this is then beta, and it's defined as the angle between the blade 0 lift line and the propeller disc plane. Our two velocities, as long as our propeller is producing thrust, combine to some resultant velocity here. We call this VR. This is our resultant velocity. So this gives us two more angles in here. Let's draw this one here. The angle between the resultant velocity and the blade 0 lift line is hopefully, obviously, the angle of attack. We can't determine the angle of attack straight away because we need to determine what this angle is here. This angle here, we give the symbol phi. Let's draw that properly and not through it. Lowercase phi. Okay, so let's define those two on here. Let's say phi is known as the advance angle. And we can define this as the arc tangent. And if we do the velocity diagram, we can see that it's the arc tangent, which is the fancy speak for inverse tangent, of Vn divided by Vr. Okay? We can probably see that our resultant angle of attack is going to be equal to whatever our inbuilt twist is minus the advance angle here. So that's beta minus the arc tangent of Vn on Vr. Okay, so this gives us the angle of attack of our blade element. It's then a function, or whatever the blade twist is, which is a function of what the setting angle of the blade is, how much we've twisted the whole blade mechanically, and then whatever the local twist due to its structure, its change of angle of attack is, minus the advance angle. And the advance angle gets bigger with the greater forward speed. Okay? So we can see here that if we go faster, the advance angle gets bigger, so our angle of attack gets lower. So if we remember now that we were going to just say here we've got CL versus alpha, we look like this. So we can appreciate, hopefully, that as we go faster, this whole thing gets bigger. So if the advance angle is getting bigger, the angle of attack for these blades is getting lower. If the angle of attack is getting lower, then we produce less lift. Now, we know that somehow the lift is related to the thrust that's produced on the propeller. So the faster we go, the less thrust that's produced by a propeller blade. We can sort of appreciate that, hopefully, from this bit here. The faster we fly, the less thrust that we produce on our propeller. And we're sort of talking about that intuitively and just looking at these equations. We'll show that when we actually code all of this up. So if you're having trouble getting your head around that, don't worry about it too much, but we will cover it. So if we were to draw our lift and drag on here now, we could draw on here what are termed our elemental lift and drag. So I'm going to write on here DL and DD. This is my elemental lift and drag. So these are the lift and drag that are occurring on this small section of the blade. We can hopefully appreciate that I've got two other instances of my advance angle occurring in here. And these will be useful when we come to resolve these forces. So this diagram here helps us relate a few things. Helps us relate the flight speed, or something that's a function of the flight speed, the rotational speed or the tangential velocity that's then a function of that. The twist of the blade, which is this one here. Let's draw that angle in here as well, actually. Let's just say beta here. Just for consistency, I'd like all of these in green. And then we can relate these to the lift and drag, because ultimately if we know what VR is, the velocity, and we know what alpha is, we can then determine what DL and what DD are. So we're going to go through some algebra to determine how can we take this diagram, how can we relate these lift and drag into our thrust and our torque. So first off, we're going to look at what are our velocities. So let's make a new slide. Hopefully you've all got a wonderful copy of that diagram and you can relate everything back to it. So our first one is Vn. This is our axial or normal inflow. So this is then just a function of the velocity that's coming into the propeller, which is the incident velocity, and then the increment that's added because of the propeller itself. So we're going to make the assumption that we've got uniform flight speed for the moment. We'll say Vn is equal to V infinity plus Vi. So this is then flight speed, and this is then the induced velocity, which is the bit that we haven't calculated yet, we haven't got a model for it, but this is the increment added due to the propeller. It's the way that it's blowing. We, as engineers, we like non-dimensional things and we like factors, so we're going to define this as V infinity is equal to 1 plus AA. So this is my axial induction factor. Now we can appreciate that's Vi divided by V infinity. That's my axial induction factor. And then the second velocity that we've got is Vt. This is our tangential velocity. This is then a function of blade rotation plus any inflow. So then blade rotation is omega multiplied by wherever the blade position is. So this is just, as long as we've got our rotational speed defined in radians per second, multiply it by where we are on the blade, that gives us the rotational speed as a translational velocity. Similarly, we then define a new induction factor, 1 minus AT. This is my tangential induction factor. Now up here we can see that this one's an addition and this one's a subtraction. We'll have a quick look at why that is. I realise I wasn't ready to explain that, but let's go through it. Let's go back and have a look at that. So we can appreciate that the actual direction of the induced velocity, if we were to look at this as a lifting line model, which we will be a little bit later, there is some induced velocity due to this lift that's occurring here and due to lift that's occurring on all the other blades. The actual induced velocity is sort of coming down in this direction. So it's positive in the direction of Vn, but it's negative in the direction of Vt. And that's why when we separate it into these two induction factors, we have a positive addition on the axial and we have a subtraction on the tangential induction factor. So these two velocity components combine to produce a resultant velocity. which we call VR. And that's just the vector sum of the two together. VR is therefore equal to the square root of Vn squared plus Vt squared. So it approaches the propeller disc at some angle, and we've already defined what that angle is. So alpha is equal to beta, which is just a structural and whatever we've set the blade at angle, minus the advance angle, which we've defined as being beta. Sorry, we defined the advance angle as being the arctangent of Vn on Vt. So we've got the start of this sort of model now. We've got things as we'd like them to look. Now, we've got lift and drag here. We assume we know lift and drag. And what we want is thrust and torque. So let's define some directions that we'd care to know about those two quantities in. So our thrust is any force occurring in this direction. And then torque is turning the blade around. So we're going to have to think about what forces are occurring that we're going to have to overcome. So we're going to say this is tangential forces. Tangential forces make the blade more difficult to turn. So if the blade's more difficult to turn, it requires more torque and therefore more power to turn it. So we're going to look at those two things. So we're going to try and look at forces in these directions. So it helps us to determine two quantities. We're going to define elemental thrust and torque. So thrust is forces occurring in this direction. The torque are the forces occurring in this direction divided by wherever the radius is. So the force contribution acting in the thrustwise direction, we can just say is dt, elemental thrust. Now then, over here, we're going to say dq. This is our torque contribution. This is going to be equal to let's say, in fact, let's go one step back. Let's say our tangential forces are our torque divided by the radial position we are at. I've not explained that particularly well there, but we'll say what we care to know, any force is going to be equal to our elemental torque divided by R. And that R value is just wherever we happen to be on the blade, whatever our radial position is. So it will help us to determine forces in these directions. So we're going to define these as dt and dq on R. So that's actually a little bit of change to how I was going to go through them, but it doesn't matter. I can change this. In fact, let's change these to two different forces. We're going to define two new forces now. So I'm going to say here. No, I'm not. Forget what I just said. We're going to proceed as I intended to. So we've got those two velocity components that give us a resultant velocity VR. It would be helpful if we could express things in terms of thrust and torque. So we can see that if we want to get the force dt in this direction, it's going to have all the forces we're trying to resolve are because of dl and dd. So our dt is going to be equal to dl multiplied by cosine phi minus dd sine phi. Now I'm being a little bit naughty here with my nomenclature. I should really be writing dt on dr is equal to dl on dr cosine phi dd on dr sine phi. Okay, so those are all the rate of change of those as we go across the span. So I should be writing dt on dr there. So let's just cross that one out. We can then similarly say here that our torque contribution, dq on r, this is going to be equal to d cosine phi plus dl sine phi. So we see on this side, our lift is positive and mostly contributing towards torque. Drag doesn't help, sorry, our lift is mostly contributing towards thrust. Drag is reducing our total thrust produced. So we want for a propeller blade it to have a high lift to drag ratio. If we look at the torque, the thing that makes the blade difficult to turn, then we see that actually, yeah, again, our drag is the chief contributor towards making the blade difficult to turn. But we can also see that actually if we produce lift, which is what helps us produce thrust, the blade gets more difficult to turn as well. Okay, and not just as a consequence of the drag that's being produced. So these help us understand why, or they'll help us understand a little bit later how our power and our torque requirements change with propeller performance. We've got dt and dq on dr. Let's go back. Did I do that right here? There we go. So if I was to define dq, then that would be simply dd cosine psi plus dl sine psi multiplied by r here. So this actually gives me dq on dr here. Okay. So we've defined these thrust and torque gradients. Now these are how the thrust and torque contributions change with the span-wise position. It would be helpful if we could stop defining things in terms of lift and drag. So let's just write these out. Sorry, stop defining things in terms of elemental lift and drag. It would be helpful if we could use the two-dimensional lift and drag coefficients. So we'll just remind you guys of what those are. So that's C with a lowercase l subscript is equal to dl on dr divided by, sorry, let's make that an uppercase, sorry, dl on dr divided by a half rho v squared c. So because it's two-dimensional, we only have a C and not an S at the bottom. And then drag similarly is going to be dd on dr divided by half rho v squared c. Those are our two-dimensional lift and drag coefficients. So we can then define our thrust and torque gradients in terms of these now. So we can substitute these into our expressions for dt on dr and dq on dr. So we can take those, substitute them into our expressions. Let's do that. So dt on dr is equal to CL cosine phi minus CD sine phi, and then we've got to multiply this by half rho VR squared. So that's just taking the thrust and torque gradient that we had on the previous page. So that's our thrust gradient here. And I've taken these and replaced them with CL and CD because we've defined these here. Now, the velocity that I'm non-dimensionalizing by is the resultant velocity. So it's important to note this one here. This is the velocity at the blade elements. And not V infinity. So we don't know what VR is yet, but it's important to note that that's the one that we non-dimensionalize these as. We can also then similarly define the same for the torque gradient. So we can say dq on dr is equal to CL sine phi plus CD cosine phi multiplied by r multiplied by half rho VR squared C. So just to make this a little bit easier, we're going to replace these expressions here. These two bracketed expressions, we can replace this with Cx and Cz, only because these get problematic to keep writing out and writing out and writing out as we do our developments. So we're going to just replace these two expressions with Cr, Cx and Cz. And in fact, we're going to work with this one, and we're going to end up with a dimensionless expression for thrust gradients, the thrust coefficient gradient across the propeller. And I'm going to leave you guys to do the same thing, or at least be certain you could do the same thing for this one. So we're going to go through that. So let's start working with this expression here. Okay, so let's just replace this with Cx in here. It's just going to be easier if I rewrite this. Okay, so dt on dr is equal to Cx multiplied by a half rho VR squared multiplied by C. C is just the chord of our local chord of our elements. And remember, Cx, we just defined it. So that is defined as CL cosine phi minus CD sine phi. So we're going to work with this expression. We're going to turn it into something that's useful. So the first thing to get rid of, the first thing we'd like to manipulate is the VR. Because as we look at this expression, we can see that VR is going to change wherever we are on the propeller. So this is then, if we just remember how we defined VR, VR is equal to the square root of Vn squared plus Vt squared. So this bit here is just the flight speed with the induction factor. We'll talk about that later. The tangential velocity, though, this is then largely a function of, so we'll say this is proportional to omega r, which is the rotational speed. So it would be useful if we could turn this into something that's constant, which would be the flight speed. So we'll have a look at our velocity triangles. So if we Vn, Vt, Vr, and the angle between these is r phi. So we can see here that Vr is equal to Vn divided by sine phi. So wherever I've got a Vr, I can then just replace it with Vn divided by sine phi. I could also then similarly remember that Vn is just going to be V infinity, our flight speed, multiplied by my axial induction factor. So that's now I can then replace this with, this is just a constant, my flight speed, then my induction factor, which we haven't determined yet, and then sine phi. So I can take this and I can substitute this term here into this expression up here, which is simplified in terms of an engineering method. It's actually made the equation more complicated, but let's substitute this in. So we'll substitute star 2 into star 1. So we get Cx multiplied by a half rho, and I'm going to have to square this whole expression. V infinity squared, 1 plus AA squared, divided by sine squared phi, and then I've got a chord at the end. So this is my thrust and torque gradient for a single blade. Propellers tend to have more than one blade. The symbol that we give for the number of blades is an uppercase B. So we can then define the total. We can say is now just equal to the whole expression multiplied by B. So dt on dr is equal to B multiplied, I'm going to bring the C over to this side, B multiplied by C multiplied by a half rho V infinity squared 1 plus AA all squared divided by sine squared phi. Just be careful here. So B is always uppercase B for the number of blades. If you see a lowercase b, it could be one of many things. In older texts, B is sometimes the semichord. It's quite useful in unsteady aerodynamics. Or B sometimes is equal to the, in some older texts, particularly in Glauert's books, B is then the chord. Very confusing. So I'm trying to be more consistent with these. C is the chord for our purposes. B, when we use it, is uppercase number of blades. And I've missed a term out in here. The bit that I've missed out is my Cx. Cx is, remember, it's Cl sine phi minus Cd cosine phi. So this is then our dimensional thrust, and our dimensional thrust gradient is then a function of the number of blades, chord, a half, whatever the atmospheric density is, flight speed squared, induction factor squared, advance angle squared, and then my my axial force coefficient that we just invented earlier. So we said that, remember that Cx was Cl sine phi minus Cd cosine phi. Okay. I'll keep hitting my head on it as well. I'll move it later. Sorry, love. This is my wife nearly running into my green screen holding string. Okay, so this is then as far as we can take this without introducing some new stuff, unfortunately. We're going to have to introduce a lot of new nomenclature today, and hopefully it would be a good start to get it written down and going forward with it. So we don't, as engineers, like to work in dimensional terms. We like to work in non-dimensional or coefficient forms because they help us compare different sized aircraft or comparable they just help us work with different sized aircraft fundamentally. So we're going to introduce the thrust and the torque coefficients. So thrust coefficient, CT, now this is where the nomenclature for propellers is someone chose to use a divisor that made sense at the time, but is discordant with some of fixed wing aerodynamics now. So we say that it's equal to the thrust divided by rho n squared, so that's revolutions per second squared, and then diameter to the 4. Okay, just got to remember that one. It's not the same as the thrust coefficient for rotorcraft. That's non-dimensionalized by the tip speed and the radius, I think. So you've got to be careful when we're going through these things. So it would be the tip speed and the disk area for rotorcraft. Just if you're not happy with how this is dimensionally consistent, just go through here and just confirm that we've got the same units on the numerator and the denominator. If you're not happy with how to do that, set up a Zoom meeting with me, we'll go through that. CQ is defined very similarly. I'll put a little triangle to say this is how these are defined. This is equal to our total torque divided by rho n squared, and we're going to put d to the 5 now because we've got an extra length term. So those are our thrust and torque gradients. Now let's change what we have in here. So these are dimensional. We're going to convert them to non-dimensional. So we'd like to now express the non-dimensional thrust and torque gradients. So what we need to do is we need to take this whole thing up here and divide it by rho n squared d to the 4. So I'll have dct on dr is equal to dt on dr divided by rho n squared d to the 4. Okay, so let's do that whole thing. Let's say that's b C rho, and I'm going to take the half here, put it down to the bottom. So I'm going to have a half rho n squared d to the 4. I've then got v infinity squared 1 plus my axial induction factor sine squared phi cx. Now I've got everything. I think I've got everything there. So this is my thrust gradient in non-dimensional form. So let's see what we've got in here because it's pretty ugly. We can see if we can come up with some useful things we can get rid of. So let's group some terms together. Let's say, okay, well, I've got this, this, and this. We're going to see if there's something we can work with here. Now we have to come up with a new expression that's going to help us. So we'll say, okay, well, what have we got here? We can probably appreciate, we said earlier, that propeller performance is a function of aircraft speed. So it would be helpful for our purposes if we had a non-dimensional measure of forward speed. So we introduce one. We introduce a non-dimensional forward speed. And we call this the advance ratio. It's given the symbol J, and it's equal to forward speed, v infinity, divided by n, multiplied by d. So we can appreciate these terms that we've brought down here, v infinity squared divided by n squared d to the 4, is equal to j squared on d squared. So we can replace some of those terms up there with some of the things that we've just determined. We're going to have a look on here as well. We're going to see what else we can, quotes, simplify by making slightly more complicated. So then we've got these two terms here. We've got the number of blades and we've got the local chord. So we're going to introduce, we can appreciate here that we've got something that's going to get bigger when we've got more blades, and if they are fatter blades, if they've got a bigger chord. So that's effectively saying if we had a lot of these, then we're trying to work out how much of the disk area is made up by blades. How much of it is solid, we could say. So this introduces a parameter that we call solidity. So we introduce a parameter called solidity. And I'm going to put in brackets, this is local solidity. And this is just a function of, at the radius we're looking at, how much of any given circle, if we were to draw a circle at any radius, how much of that would be made up by blade, how much of it would be made up by thin air. The ratio of blade to not blade at a given radius. Now, it's not quite true to say that, because obviously if we were to do the ratio of blade to not blade, we'd be looking at including the twist angle, because then we'd be looking at how that's projected into the disk radius. In fact, we just say that we've got this parameter, which we have the symbol sigma. Sigma is equal to BC on pi multiplied by r. So we can see here, also it's not actually the proper ratio of the two, because if it was the proper ratio of the two, it would be over 2 pi r. But in the vagaries of propeller literature and how things have developed, and hopefully you remember that salient quote from Quentin Wald, that the literature of propeller aerodynamics is scattered and in some respects inconsistent and incomplete. This is where things like this come from. So solidity is this dimensionless measure of how much of the disk area is propeller, but it's not actually the ratio of that. It's the ratio of how much of half of the disk area is made up of all of the blades. Just remember this term, write it down, we'll be using it. Okay, so this is our local solidity here. So we can see that accordingly, BC is equal to our solidity multiplied by pi multiplied by r. So I can take these two things, I can take this here and substitute them into our expression. So we're going to say this one's going in and this one's going in as well. So substituting solidity and advance ratio into our expression. I've just seen I've hit about an hour of recording, so I'm going to, just in case the audio's gone out of sync at any point, that will help me bring it back. So we're going to substitute the solidity and the advance ratio into our expression for the thrust gradient. So we have dCt on dr is equal to the solidity multiplied by pi multiplied by r. So that is what was previously BC. We're then going to put j squared, because this is where our advance ratio, we had j squared on d squared. So we're going to combine things in the denominator, 2 and d squared. And we're then going to have 1 plus a squared divided, that should be aa squared sine squared phi cx. So this is looking somewhat tidier now because we've introduced all these extra terms in here. We can probably appreciate, remember that r is equal to, let's just check I'm going right with this. I might overly complicate this, but we'll go through it. We can say r is going to be equal to our non-dimensional ordinates multiplied by our total radius. So that's equal to x multiplied by d divided by 2 in this case. So if we substitute that in, we get sigma multiplied by pi multiplied by x multiplied by d on 2 j squared 1 plus AA squared 2 d squared sine squared phi multiplied by cx. So we've now got d's that we can help cancel, and we can bring this 2 down to the bottom as well. So I've got sigma pi x j squared over 4d 1 plus AA squared on sine squared phi cx. I tend to keep these as 2 fractions just because that's how I have always derived this, and it helps me remember it. Okay, so what we've got here, this is now dct on dr, still dct on dr. We've got this x here. It would be helpful if we could get rid of this x. So let's have a look at what we've got here. We've got sigma and we've got x here. So if we take these 2 terms and we multiply them together, we remember that sigma is our local solidity, bc on pi multiplied by r, and x is r divided by r. So this gives me some new term, which is bc on pi uppercase r, where remember uppercase R is the radius. So we call this sigma r. I've called this modified solidity here. I've never found a name for this particular term. Modified solidity. Okay, and we can see here hopefully that we could just replace d with 2r as well, and that's going to help us. So we substitute these 2 things in. So we substitute where we had sigma and x, we can replace this for sigma r, and where we had d, we can replace this with 2r. So dct on dr is equal to sigma r multiplied by pi multiplied by j squared divided by 8r 1 plus AA squared divided by sine squared phi multiplied by cx. And we can remember that cx is simply CL cos phi minus CD sine phi. So we've got an expression for our thrust gradient now. It would be helpful to, this is still in terms of a dimensional thrust gradient because we've got a dimensional numerator. It would be useful if we could then just have this over dct on dx, which is then this non-dimensional span-wise ordinate. Remember x is equal to r divided by r, which is our span-wise non-dimensional ordinate. So dct on dx would be equal to dct on dr multiplied by dr by dx. Okay, so dr by dx, r is equal to x multiplied by r. Therefore dr on dx is simply equal to r. So if we take our expression and we multiply it by r, we get dct on dx. So we take this, multiply it by r. So dct on dx is equal to sigma r multiplied by pi multiplied by j squared divided by 8 multiplied by 1 plus AA squared divided by sine squared phi, and I'm going to expand my force term here. So I'll say CL sine phi minus CD cosine phi. This is my non-dimensional thrust gradients for a propeller. and let's see the things that it's a function of. So it's a function of this this modified solidity. So sigma r is equal to b c on pi r. We've got pi on the top as well. Does that go? No, it doesn't. We've still got pi in it. Pi still exists in this expression. Let me just check I haven't made a mistake here. Go back to my own notes. There we go. There should be a pi in there. It's then a function of the advance ratio. J is equal to V on ND. Phi, which we know is the advance angle, phi is equal to the arctangent Vn on Vt. And then AA, which is the axial induction factor. So we've got this expression here. It's taken us about an hour and a quarter to get here. This probably would have been maybe a week or two in a regular course. I've gone through this because I want you guys to follow as we're going through. I wouldn't necessarily, well, I certainly wouldn't expect you to be able to do this on your own, but we are developing these expressions such that we can use them. I would appreciate it if you guys could determine the non-dimensional torque gradient. That's just the same. dcq on dx is equal to sigma r pi j squared on 16 1 plus AA squared sine squared phi CD. Right, I just made this mistake up here. Those two aren't right. Let's erase those. The sine and the cosine were switched around up here. Something seemed wrong when I first wrote it. Let's erase those. There we go. That's correct now. So this time they've got to be reversed down here. Man, this is lagging today. So we've got CD cosine phi plus CL sine phi. So you can probably appreciate that we've got this down here. It's got a factor of a half effectively. So remember that CQ has got, so we would look at, if we were to effectively look at CQ divided by CT, it would be D. Okay, so there's an additional dimension there, and then so it cancels with the additional radius to give us the factor of a half there. Okay, so we can go, if you want to go through and derive that and just check that you could get to this stage yourself. Okay, so we've got these expressions now that we can use to determine propeller performance. Now, they're not that useful just yet because we don't quite know what they mean. We still don't know how to get lift and drag for a propeller, but we've made a good start. We've got something that we can eventually code up and we can use to determine propeller performance. So we're doing pretty well. We've got here, we don't know how to determine the induction factors yet, so we're going to take a few guesses and we're then going to play around with these codes in tomorrow's lecture and see what we can get out of these. Okay, so a lot of new stuff today, a lot of new theory, and we've gone through things at a relatively fast pace because I know you guys can go back and review review the lecture as you see fit. Take your time to go through it. If there are questions, please put it up on Slack. Again, I'd prefer if you could ask in a public place, so don't feel stupid. We all ask stupid questions from time to time, and I'll never call you out for it. I will appreciate knowing how people are understanding this theory. So thank you for your time today. I will see you all tomorrow. I'll deliver one, maybe two more lectures this week so we can go through this stuff, and we're going to start doing some real coding in the next couple of lectures. Thank you guys. Enjoy your day. I'll see you all soon.